Good morning. I'm going to go over a couple of interesting things about the BioGem circuit. Okay, so right now the meter is 0. The capacitors are shorted. So I'm going to disconnect the capacitors. And I'm going to hook up BioGem. And it immediately fills up the capacitors. Remember what BioGem is. It's gold and graphene fused together, and then I use this graphene that I dropped from CO2 as a capacitive. The cell is just a real simple demonstration cell. Here's one, stainless steel on one side and aluminum on the other side to disprove a galvanic reaction. So we have 600 millivolts, but this is what's interesting. I'm going to hook up this variable resistor here, and there's our millivolts and resistance. So I'll bring this over here so you can see it. And I'm just going to adjust the rheostat. And as I give it more turns, get the amperage to come up. There we go. It's 100 kilo ohm rheostat. The voltage keeps going down, but the amperage is kind of holding. See that? It's very interesting. You can peg the amperage. Oops, I put the cell together here. It's just a taped together cell, so put a little bit of pressure on it. I'm just going to put a little bit of weight on it. Okay, that's a better reading. So we have 10 microamperes at 120 millivolts, but watch the gauge. It's like it self-regulates. So I'm going to turn down the resistance. See the voltage climbing, but the amperage is not really moving. It's really interesting. it's like it's keeping up through the capacitors, because I've got the voltmeter down here at the end of the capacitors, and I have the resistive load at the end of the capacitors. See how the voltage goes back up? I'm under a standing load, and the voltage is climbing. That's really interesting. So we're going to leave it here for a second, and we'll see what the voltage will climb up to. The amperage is really, really steady. It's almost no draw at all. But the voltage keeps climbing up under load. Okay, while we wait for the voltage to climb, I want to put your attention to this. See those little holes there? Those are 10,000th holes, and this is a piece of silicon carbide that'll be the blank for our new BioGem chips. And then here's an example of the machining that we can do. This is a toroid on a fly's head cut out of the laser machining. Isn't that cool? Okay. So back here to the voltage. And the amperage has not moved. We get 315 millivolts, 14 millivolts at 4.5 microamperes on a standing load. It's like it's filling up the capacitors as the load is being drawn from the resistance. It just fills up the capacitors. So we're going to give it more load. Sorry. We're up to, I'm twisting on the rheostat. Let's go to an even 10 microamperes and see what that does. There we go. Well, that was interesting. It's like it jumped up all on its own. Look at that. I gave it full load and the voltage went down, and now it's filling back up. So BioGem is filling up the capacitors. Okay, so now we're at 10 microamps. See it self-regulate? And 100 millivolts. This is the phenomenon that BioGem does. It will self-regulate. So if you dead short it, the energy comes right back, but if you put it under a constant load, it wants to keep that load up. This is pretty good from one drop, maybe 2 drops of the solution, and you guys have seen the earlier videos where I built these on demonstration. I'm not moving, my hand is over here, see? I'm not moving the needle. It's self-regulating all by itself. It's extremely interesting. We're into this video 12 minutes under a dead load. Let's see, the amperage drops down. Let's see if it'll jump back up again. There you go. It jumps back up based on the resistive load. Okay, so here's what's going on here. During the resistive load, it's trying to keep up with the impedance, which is the AC part of the DC output of the BioGem. The voltage jumps back up. And let's see if the amperage will jump up. There, the amperage is jumping back up. And look at the voltage jump back up. By now you're probably bored of this video, but this is kind of what observational science is. It's boring, and studying the anomalies to try to turn these into science. I just think it's interesting that it self-regulates, and it's working through these capacitors. These capacitors are not the biggest, but they are 2000 volts at 0.85 microfarad. So they're pretty fast reacting, and they've got some capacitance to them. You would think under a dead load it would just continue, the voltage would continue to go down, 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 coinciding with the amperage, but it doesn't do that. I don't want to upset the circuit, but this is a I'll get another one. I have another one right here, handy. It's a pretty nice variable resistor. So now look at the voltage and amperage. It's going up. I've always kind of said this before, you have to kind of trick the voltage out of these cells, because if you dead short them, they'll just go into a closed loop, self-resonating loop, and that is the phenomenon about graphene. It's like a PNP transistor, it will self-regulate. So if it's got something to do, it's more than happy to do it, but if you dead short it, it really won't burn itself up. I'm not moving the needle, by the way. It's just, that is self-regulating by itself. It's trying to raise the voltage up. So we're into this video 17 minutes. We could do a calculation by the hour of how much energy this one drop of solution can put out. So I made the setup today so you guys can see the self-regulating aspect of BioGem, and that it will actually keep up with the load. It won't deplete like a battery because it is an energy generator. So I've talked about this before in longhand, but it's real simple. Graphene is a six-sided hexagon two-dimensional crystal. It's an allotrope of carbon. It's superconductive. Gold and graphene go together. The Nano Science journal published a couple years ago that gold and graphene can go together. They just don't know what it did. Since I've been working with it so long, I realized that the fluid is superconductive at room temperature. So it pulls energy at room temperature. The single atom gold has an elliptic shell in its outer electron valence, and that outer electron goes around the graphene just like a generator, and it generates electricity. We have one metal on the periodic chart that does the same thing. It's rhodium. It has an elliptic shell in its outer electron. Rhodium is found in trace amounts in gold and silver wells. But you're watching the self-regulating principles of BioGem. It wants to hold and maintain that load . It's pretty impressive. I'm going to move this over here so you guys can see that I'm not actually moving the resistor. Oops. messed up here. Sorry, I did something wrong. What did I do? I disconnected something on accident. I don't know what I did. Hold on. Oh. I disconnected this on accident. Sorry. Okay. We're back at it again. Give me a second. I'm just adjusting the resistor because I got it all messed up. Move this over here. Okay. Sorry about that. You can still see it's keeping up quite nicely. And remember, this is just a little taped together cell as a demonstration, so you have to put a little pressure on it. It even makes more amperage. Lithium-ion battery, I believe, is under huge amounts of pressure. Okay. So just a quick little disconnect, and it regenerates more electricity. It's still a standing load. I think that's pretty impressive. And we're into this video 22 minutes. And we're not seeing any depletion of the cell. In fact, the longer it runs, seems like the better it gets. Okay, for 1 second, what we're going to do is we're going to disconnect the resistive load, and we'll see what the volts go to. Remember, there's no resistance going into capacitors, which is the beauty of BioGem, is that you can fill capacitors with no resistance, and the voltage under a dead load, we just disconnected the resistance, and look at the voltage jump back up. It's really impressive. So we won't move the potentiometer, and we're going to see what it looks like when it jumps back up to the original voltage. I think it's 640 millivolts. Oh, and don't forget, the meter is additionally taking sample voltage, so that costs you joules when it's doing that. So as the meter's even sampling, it's drawing down voltage at a pretty good rate, and this BioGem is still compensating for the meter and adding voltage to the circuit. So while we wait for this to fill up, there's only one drop in the cell. I wonder how much voltage is actually potentially available in this. Oops. Oh, I see I have a loose connection here. I'm going to tighten up this connection a little bit better. Okay. So we get 635 millivolts. I believe this is a non-shunted microamp meter. That's why there's no amperage being drawn. It's running through the meter now. Alright, so we're at 640 millivolts again. Meter sampling, load disconnected through the capacitors. We're going to reconnect the load. You ready? Okay. 642 millivolts, and here comes the load. Now remember, we didn't move the potentiometer. So at first we get an amperage draw, and we get a voltage draw. We haven't moved the potentiometer yet. It's trying to keep back up with the resistive load. So I'm just going to put a little bit of weight on the cell. Okay, it's not really changing much. We'll stop this video at 30 minutes. I think 30 minutes is a pretty good indication of my claim of BioGem being an energy generator. All the persistent currents are there. All the different definitions of superconductivity are there within all the studies of BioGem and basically how it's made and the results. So right now the world is looking at room temperature superconductivity as zero resistance, but what I've realized is that room temperature superconductivity makes electricity. That's a plus, in my opinion. Well, I hope you enjoyed this update of what BioGem is and what it's capable of. Pretty much the best presentation I can do for you under a resistive load. Thank you very much for watching, and have a good day.